All right. So yeah, we're picking up with the chain rule. Just finishing what I didn't deem practical to do all in one day yesterday. Um, so yesterday's chain rule, I gave it to you guys in the rule in function notation. Today I'm giving you guys an alternate version that uses Leibniz notation that is useful at other times. Let's dive in. Now you might recognize this function from yesterday. We actually found this derivative yesterday using the chain rule. And you guys already could have found this derivative from several days ago using the power of a function rule. But we're going to approach it a different way. So you can think of y equals the root of 4 minus x squared. You can think of it as a composite function. Y equals root u is the outer function, and the inner function is u equals 4 minus x squared. Can you guys visualize that? Outer function, inner function. So the chain rule says differentiate the outer function, root u, with respect to the inner function. So basically, we're finding dy by du. And then we multiply by the derivative of the inner function, which would just be du by dx. And these two derivatives aren't too overwhelming for us to do. We can crank those out. Now, the derivative of root u, we've done many times. We've done lots of times, but I have lots of space here, so I'll just do the full derivative. Remember that root u is like u to the power of a half. So I'll show all my work here, but this is like one of those derivatives where at this point I'd probably be okay if you just went right to the derivative. But for dy by du, we bring down the 1/2, we take 1 off the exponent, and that's the derivative. Of course, the u to the 1/2 goes in the bottom, and that's just 1 over, oh, I missed a 2 there, pardon me. It's 1 over 2 root u. So we've done that derivative like many times, probably like 3 times already. So if you can just go right there, that's totally fine. Yeah, it's dy by du. Du by dx, so u equals 4 minus x squared. That's not too bad. Just bring down the 2. So that derivative is minus 2x. And so the chain rule says you multiply these two things together. So therefore, dy by du times du by dx would look like this. It would be 1 over 2 root u, and then you're multiplying by negative 2x, and we can divide out those 2's there. And so what you get for the derivative is, I'm going to be naughty here. Don't tell Miss Plattner when she's here next week that I did this. I'm going to go left to right, more than one equal sign per line. We get negative x over the root of u. And if we remember that u is equal to 4 minus x squared, that's just negative x over the root of 4 minus x squared. So I might just add a little note here in purple. That's since u is equal to 4 minus x squared. But if you guys, I think many of you guys have your binders there. If you guys look at yesterday's note, we already did this derivative. You get the same derivative because we're using the same chain rule, just framed in a different way using Leibniz notation. So same derivative. Let's actually kind of restate the chain rule if we're using Leibniz notation for our derivatives. And this is actually where the chain rule gets its name. It's pretty cool. So observe. So if you have a composite function, so y is a function of u, but u is a function of x, then the following is true. If you're doing dy by dx, this is equal to dy by du times du by dx. And do you see how it kind of forms a chain? You can almost think of it as like the du's kind of like divide out to 1, and you're left with dy by dx. This is why it's called the chain rule, because you can kind of form a chain of derivatives. So this is essentially what we did yesterday, but just using this Leibniz notation. Now, I think I mentioned, yes, I do mention this. So these aren't actually fractions, and the du's don't actually equal 1 when you divide them, because dy by du is just like a thing. It's like a whole thing. You can't like separate it or do anything with it. But it's just, if you're just thinking of it as a memory device, then yeah, think of it as du over du divides to 1, and you're left with dy by dx. So very cool. It's the chain rule in Leibniz notation. It's how it gets its name. And we're just going to do a few examples today, playing around with the chain rule again, just with Leibniz notation instead. And I think my last example, we do 2 different ways. We'll see. Maybe if I have space, we'll do this one 2 different ways. You know what? We're going to improvise. When you guys teach your own math classes, you are not going to do what I'm doing and improvise, because it rarely works out. But today it's going to work. We're going to do this 2 ways. We're going to use the Leibniz version of the chain rule, and then we'll maybe do it a second way, because I think we have the space and the time. All right. So let's use our new Leibniz version of the chain rule. So what is dy by du? I don't think we need to do a lot of work here. We already did the derivative of root u up top. So the derivative of minus root u would just be minus 1 over 2 root u. If you guys are okay with that, we already did that up top. So now it's just minus root u. All right, and then du by dx, I'm just going to fit it in here. We're forming that chain. 12x squared minus 6x, and the derivative of 1 is 0. All right, so chain rule says that dy by dx is equal to dy by du times du by dx, and we've just found those 2 things, so we'll replace those, and then we'll do any simplifying. So dy by du minus 1 over 2 root u, and then we're multiplying 12x squared minus 6. And if you guys are okay, I think we'll go right to our final answer. So hopefully you guys can visualize we're going to be doing 12 divided by 2 and 6 divided by 2. Every term in the top has a 2 in it. So 12 over 2 would be 6, and then 6 over 2 would be 3. And then we're going to have root u on the bottom, but u is just equal to that cubic polynomial. And so what we end up getting is negative 6x squared. I guess I'm switching to pink now. And then we have negative 1 times negative 3x, so plus 3x, all divided by the root of u. But u is just equal to that 4x cubed minus 3x squared plus 1. So do each individual derivative, multiply them according to the chain rule, and then just tidy things up. You guys okay with that? Yes, Kaya. You sure? Okay. All right, so that was method 1. Method 2 would be to approach it using stuff from several days ago. So, or why don't we just write y as a function of x? So y is equal to negative root u, but u is equal to 4x cubed minus 3x squared plus 1. So we can actually just put the inner function in, actually replace u with what it's equal to, and now we have y as a function of x. We can write that as a power, and then this is just a good exercise in finding derivatives. Can you guys try finding that derivative, dy by dx? And we should get the same thing as before. Actually, that worked out really nice spacing-wise, so I think I'll just start doing that all the time. You know what, you guys, I'll pause the recording. You guys get a head start. I'll do attendance, and then I'll come back. All right, let's find this derivative using the power of a function rule, i.e. the chain rule. So bring down the half, we're left with minus a half. Leave the inside alone is what the chain rule says. Take 1 off the exponent, minus 1/2. And the derivative of what's on the inside, 12x squared minus 6x. And then you basically see everything we already did is right there, right? We've got 4x cubed minus 3x squared plus 1 to the power of negative 1 over 2. Well, that just means it goes to the bottom, and the 1 over 2 exponent means it's square rooted. And again, we have negative a half times, maybe I can do this, negative 1/2 times 12x squared and times minus 6x. You get exactly what we had before. You get negative 6x squared minus a half times negative 6 is plus 3x. On the bottom, you'll have the root of 4x cubed minus 3x squared plus 1. Which method do you prefer? You could probably make a case for either method. It's really just whatever you're comfortable with. Both are fine. I think for this next one, to manage my space, I didn't leave a lot of space for this next one. So I think I'm going to just pick method 1 intentionally here because we're doing something a little extra with the next one. Before we move on, anything you guys want to chat about? All right. So in this problem, very similar problem, y is a function of u is a function of x. This time, we're going to evaluate the derivative at a specific value. So I want to use that first method with you guys and show what that would look like. If you were to use the second method, you could do the same thing. Replace u with what it's equal to, find the derivative, and then once you have dy by dx, plug in 2. But what would that look like using the first method? So I just want to show you guys. So I'm going to try to manage my space really well over here. So we're going to do dy by du first. And, oh, that was nice of them to write that as a power for us. So bring down the minus 3. Take 1 off the exponent. So minus 3u to the power of minus 4. And we'll just be naughty again and just write that left to right as minus 3 over u to the power of 4. And then du by dx, that one doesn't look too bad. So the derivative of 2x is 2. Derivative of x cubed minus 3x squared. And then we are ready to find dy by dx. So we take, I'll show this step, got the space. Dy by du, multiply by du by dx, i.e. a chain of derivatives. All right, and if you guys are okay, I'm just going to multiply. I'm just going to just do the multiplication. So we're going to have minus 3 times 2 minus 3x squared. And on the bottom, we're going to have a u to the power of 4. That's just what I get when I multiply those two derivatives together. Now we have to find the derivative dy by dx when x is equal to 2. So we can plug in x equals 2 there, but like, what do we plug in for u? So as a little aside, I'm going to do this down here. I'll just put a little aside. We just gotta ask ourselves when x is equal to 2, what does u equal? So but that's not hard to calculate. U is equal to 2x minus x cubed. So 2 times 2 minus 2 cubed, whatever that is. I think it's negative 4. And now we're ready to finish things off here. I think I'll do it. You know what? I think I can keep things clean if I do this over here. So our goal in this question is to find dy by dx evaluated at x equals 2. And now we can just go ahead and do that. So minus 3 times 2 minus 3 times minus 4 squared. Excuse me, x is 2, right? X is 2. And on the bottom, it's u that's minus 4. And so this is just some order of operations, some calculator work. could probably just do the top and bottom separately. Minus 4 to the power of 4. I can do that this morning. 256. The top. Can I do the top? Yeah, we can do the top. Because 2 squared is 4. 3 times 4 is 12. 2 minus 12 is negative 10. Times negative 3 should be 30. 30 over 256. We can reduce that, I guess, to 15 over 128. You guys have your fraction buttons. You can see if that reduces any further. I don't think it does. Since 128 is a power of 2, that would also give you a nice decimal, but I think I'll leave it as 15 over 128. You guys okay with what we did there? Okay, just I don't have space, but alternatively, we could have done something similar to as method 2 here. Found the derivative that way, and then just plugged in 2 everywhere. Would that have taken up more time? Who can say? All right, you guys sure we have the time if you guys have a question or two? All right, well, in that case, we're going to do an application of a composite function, and we are going to do this one 2 different ways because we have the time and we have the space. So here we have a mountain climber just walking in a straight line, carrying a thermometer, kind of climbing up a mountain. So I think everybody at this age understands that as elevation increases, temperature decreases, right? Well, I guess chemistry people would be like, well, if the pressure changes, could be different. But no, just like all things considered, the higher you get, the colder it gets. So temperature depends on altitude. But this mountain climber's altitude is changing with time. So the temperature this mountain climber is experiencing is varying on the altitude, but her altitude is changing with time. So this is a composite function. We have how the temperature changes with altitude. Down here, we're just saying it's a quadratic function. And we have the mountain climber's altitude changing as a function of time. So we're going to find the rate of change of temperature as a function of time. So basically, is it getting warmer every hour, getting colder every hour? Like how fast is it getting colder? We're going to find that out after 4 hours of climbing. And we now have 2 methods to do it. The first method we're going to use is we're going to express, right now, the temperature is a function of altitude. We're going to get the temperature as a function of time. So then we can just find that derivative directly and plug in 4. So here we go. This method is, if you're really comfortable with your grade 10 math and just expanding, simplifying, method 1 is not too bad here. So let's dive in. So how do we get the temperature as a function of time? Well, we take the temperature as a function of altitude, which was negative 0.1 times a squared, but a is equal to 0.1 t plus 1. And we'll square it. Minus 0.2 times a, but a is equal to 0.1 t plus 1. And minus 5. So I'm going to, this is just quadratic. I'm going to expand and simplify, collect like terms. But yeah, again, if you're not comfortable doing that, like we should be comfortable. But if you're not, this method might not be your cup of tea. Binomial squared. So we're going to have 0.01 t squared. And then we'll have 0.1 t times 1. And then the same thing again. So 0.2 t. And then 1 squared is 1. And then we have minus 0.02 t, just using the distributive law here. And then minus 2 times 1, minus 0.2, and minus 5. One more distributive law, and then we can collect all the like terms together. And then we're just going to have a nice, tidy little quadratic function to find the derivative of. So let's just be careful. I'm living dangerously. I'm just doing mental math here. I'm not even peeking at my notes. 0.001 t squared. Negative 1 times 0.2 is negative 0.02 times t. Negative 1 times 1, negative 0.1. And then our other stuff. Negative 0.02 t, negative 0.2, and negative 5. And then we'll time travel back to grade 9 and maybe underline our like terms. This isn't necessary. I know that you guys can collect like terms. All right, we did it. Negative 0.001 t squared minus 0.02 t and another one makes minus 0.04 t. And then minus 0.1, minus 0.2, minus 5, minus 5.3. I think that's good. Now, that wasn't fun to do, but it really is just grade 10 expanding and collecting like terms. Shouldn't be a huge deal for us. But now it's at a point where we can just find the derivative. Bring down the 2, negative 0.002 t, and then minus 0.04, and the derivative of negative 5.3 is 0. So that's it. And this question wants us to find the rate of change of temperature with respect to time at 4 seconds, and we can now do that. Plug in 4. T prime at 4, negative 0.002 times 4, minus 0.04, and that would be negative 0.048. And the temperature is in degrees Celsius, and the time variable is in hours. So our mountain climber at this specific point in time, the temperature is getting colder, not by too much though. Instantaneous rate of change is about a 20th of a degree Celsius per hour at that point in time anyway. It could be like a flatter part of the mountain. You guys okay with what we did there? All the skills you guys have the skill of expanding and simplifying. It's the derivative is not too bad, and then just plug and play. Now let's use the Leibniz version of the chain rule, and then you guys can decide which method you like better. So here we go. So the chain rule says if we're looking for the rate of change of temperature with respect to time, we can do the derivative of temperature with respect to altitude, and then multiply by the derivative of altitude with respect to time. Now those two derivatives are not that complicated to do, because dt by dA, that's just quadratic. So bring down the 2 times negative 0.1 is negative 0.2. Take 1 off the exponent, you're left with a. And then the derivative of minus 0.2a is just minus 0.2. That's that derivative. dA by dt is even easier because that's just a linear function and its derivative is just 0.1. And now we're just ready to plug in. The only thing with this method is we're asked to find this rate of change when the time is 4 hours. There's no little t to plug in 4 in there. We just have to find the altitude after 4 hours and plug that in, which is it's not that hard to do. So when t equals 4, the altitude is equal to positive 0.1. 0.1 times 4 plus 1. So after 4 hours, the altitude is 1.4 kilometers. And now we're good to go. So now we know what to plug in. So the question wants the change in temperature by the change in time evaluated when t equals 4. We're now good to do that. So I'm going to just use some square brackets here. So we have negative 0.2, lots of negatives floating around, times 1.4 minus 0.2, and then multiply that by 0.1. And then cross your fingers, we get the same answer as before. We should, because math makes perfect sense all the time. I'm eyeballing this, and I'm 75% confident this is going to work. Negative 0.2 times 1.4, negative 0.28. Aha, yep. Minus 0.2, negative 0.48, multiplied by 0.1. I could even show an extra step there. Yeah, you get negative 0.48 times 0.1. Of course it worked out. Degrees Celsius per hour. Now I'm going to zoom out to take both of those in. Which method do you prefer? Method one was a bit more grindy, but the skills you use are kind of just expanding and simplifying. That was the trickier part, if you want to call it that. Method two, I think, was pretty slick. However, it does require pretty good knowledge of using the chain rule. So in practice, you guys can pick. Anything you guys want to chat about? Congratulations, we got through the first unit. It does stretch out. It stretches out every year, especially because we do this in the wintertime. So weather often affects things. We do start off slow. So I appreciate you guys. You've done a good job. I'm going to pause the recording. Not pause. I'm going to end it.